Hello, here's another problem. Okay, this one has an RLC circuit in it. I should have probably mentioned it's an AC RLC circuit. It's driven with a frequency of 60 hertz, so I guess that kind of tells you it's an AC circuit, and an RMS voltage of 120 volts. It has 250 ohms resistance, and the inductance is zero point 0.1 henries. The maximum current in the circuit is 0.5 amperes. And then we're going to calculate a couple of things here. We're going to calculate the capacitance in the circuit, and we're also going to calculate the maximum voltage across the capacitor. Okay? Now, first off, there's a whole bunch of equations involving RLC circuits, and I've written a bunch of them off to the right there, just so that you can see them all. Okay? And we're going to try and pick out the ones that we're going to need here for this problem. Okay? So let's see. We want to know the capacitance in the circuit. Okay? Basically, the way capacitance figures into the circuit is here. Okay? Through the capacitive reactance. Okay? And the way we're going to so to figure out the capacitance, we're going to have to figure out what the capacitive reactance is. And we got a couple of equations with capacitive reactance in it. We've got this one, okay, but we don't know what this is. This is the RMS voltage across the capacitor. We don't know what that is, okay, so we can't really use that. All right. The other one is we've got the capacitive reactances in this impedance formula, and the impedance we can actually figure out from here, okay, because we have, or we can get, we've got the RMS voltage, and we can get the RMS current, so we can get the impedance. So that's how we're going to work through and get the capacitive reactance here, and then the capacitance. So let's start with that then. Delta V RMS equals I RMS Z. Okay, so notice this is the power supply voltage. Okay, that's what's related to the current by the impedance. All right, a lot of people would be tempted to use this. Okay. To figure out, well, in a situation like this, but this we don't know. This is the maximum voltage across the resistance, and what we know is the power supply voltage, not the voltage across the resistance. So anyway, let's see, delta V RMS, this is 120 volts, okay? I RMS, notice what we've got here is the maximum current. So this is I max divided by the square root of 2, which works out to about 0.354 amps. Okay, so in other words, it's 0.5 divided by the square root of 2. And so this is 0.354 amps times Z, and that tells me that Z, my impedance, is equal to, let's see, there it is, 339 ohms. Okay? And now we're going to use that to figure out what the capacitive reactance is, because we know what the resistance is. It's 250 ohms. The inductive reactance, we can figure that out. Okay? XL equals 2 pi FL equals 2 pi times 60 hertz times 0.1 henries. And so XL then is 37.7 ohms. Okay? And so we've got everything in here except XC. So I'm going to have to solve this for x sub c. So let me start by squaring both sides of my equation. So this gives me z squared equals r squared plus xl minus xc squared. Okay? That means 339 ohms squared equals, let's see, 250 ohms squared plus 37.7 ohms minus x sub c squared. And this gives us 37.7 ohms minus xc squared equals, let's see, 52,700 when we square that and subtract. And my units are ohms squared. And so if I take the square root of both sides, I've got 37.7 ohms minus xc. Now I got to be careful here, okay? Because if these two things are going to be equal, then this can either equal the square root of that or negative square root of that. So this is actually, we don't know yet, this is going to be either plus or minus, what is that, 230 when you take the square root of that. Okay? Now, it turns out in this case, only one of those is going to make sense, okay? Because, see, x sub c here, that's got to be a positive number. So there's no way we can get something above 37.7. So this is going to have to be negative. So negative 230 ohms is equal to 37.7 ohms minus xc. And this gives us xc is equal to 267 ohms. Okay. In other words, if I'd have taken plus 230 ohms here, I would have ended up with a negative number for x sub c, and that can't be right. Okay. Anyway, the capacitive reactance, let's see, we know that from up here, so that has to equal 1 over 2 pi f c. Okay. And of course, f is 60 hertz. And so when I plug all that in, I get that the capacitance is 9.92 times 10 to the minus 6th farads. Okay? So that's the first thing we said we were going to calculate. Okay? We said we were going to calculate the capacitance in the circuit. And then the other thing we want is the maximum voltage across the capacitor. Now, the thing I want to point out here is that you see I've written all these equations that relate like delta V something RMS to I RMS, right? There's one, there's one, there's one. There's another one I haven't bothered with for the inductor, okay? All these equations that relate the RMS voltage across some device to the RMS current, okay? Those work just as well if we're talking about the maximum values, okay? Because the maximum values just differ from the RMS values by a factor of the square root of 2. So I can say delta VC, this is the voltage across the capacitor, max is equal to I max times x sub c. And this is 0.5 amperes, okay? Notice this says the maximum current in the circuit is 0.5 amperes times x1, or times the capacitive reactance, which we just found to be, where'd that go? There it is, 267 ohms. And this gives me the maximum voltage across the capacitor is 133 volts. And that's the other thing we were going to calculate.